segment with endpoints on the circle.
Thanks, Madison.
Segment with the endpoints on the circle. Nothing crazy, nothing fancy. This is nothing new. Okay. So what we've done before, excuse me, is that you'd say that CB was a chord. It was just a segment. Now that segment would have a bar over it, because segments have just a little single line on it. It also has an arc that it runs into. Chords create arcs, if that makes sense. Okay? Chords create arcs. It's called an intercepted arc. Okay? It's where the endpoints create the arc. All right? They can go all around the circles. Remember, we had major, minor, all that kind of fun stuff. Too. Okay. The most famous chord of them all, it's called the diaphragm.
I bet you were going to have like a music.
Yeah.
I was like, okay, I'm trying to think like what song is he referring to? Yeah, sorry.
That's oh. That's my eye. All right. We know that. Don't worry about that. Congruent arcs. Excuse me. If in congruent circles, remember, if circles were congruent, they had to have the same radius. Remember that? That's the only way that the circles can be congruent. What happens then is that in the same circle, or in congruent circles, two minor arcs are the same if their chords are the same. So what happens here is that if you get when you get a circle, and this makes total sense if you look at it. Actually, yeah, that. So if I take the 8 iron of death, yes. If I take the 8 iron of death, and I say I'm looking at it from this piece to the hosel, in case you guys didn't know that, what that was called. What are they called?
What's it called?
Hosel. So from this part to here, where my fingers are, that's the same distance. That's just a measured distance, right? So if I'm hitting this circle here where those two endpoints are, that arc is created. Are we okay with me on that? As I move this along, it's not touching endpoints anymore, is it? Until I get back down to here. Once I get back to here, that just means, and I don't know if you can see it, I kind of erased where the endpoints would have been at. That just means that these two arcs would be the same length. They're the same value because the segment part was the same. And it makes total sense if you start thinking about it. If you take any segment in a circle, let's see if I can undo this real quick. Oops, sorry. If I take just this segment here and I move it down to here, that has to be the same amount of part of the circle that's been intercepted, if you will, that's it's touching. Because that segment length doesn't change. So that segment length doesn't change, wherever else it hits within that circle, it still has the same amount of arc to it. Does that make sense? Also, what you can do, let me move this back up, is if I draw to the endpoints here and here, what do I create? Triangle. More specifically, what do I create? Isosceles triangle. It could be obtuse, I don't know. But it's isosceles because what are those two segments going from AC to AB? Radius. They're congruent, right? So what happens is these are going to be the same because they're radii. Okay, plural of radius. Excuse me. Which means that if I take the same exact segment and I move it down to here, I'm still going to get the exact same thing going this way, which gives you congruent triangles. And if you have congruent triangles, you have all the corresponding parts that go through it, which means that you get central angles that wind up being the same, which means central angles, arcs, are the same. So it all boils back down to congruent triangles. That's where all of this stuff comes from. Okay? I know it's kind of a long-winded explanation, but if you take a circle and you just take your pencil and you see where it touches, that same where it touches in one spot is going to be the same on any other portion of the circle as you move it around. That's all it is. Okay? That's all that means. Is that clear? It sounds weird, but does that make sense? Which then means we can do stuff like this. Excuse me. You get into some stuff that really winds up being a lot of no-brainer math, to be honest with you. When you have the curve over the letters, what does that mean? It's the arc, it's the curve part. And it being within degrees, that means it would also be the measure of a central angle. So if it says that GH, the arc of GH is 110, or excuse me, is 100, that's this intercepted arc. That chord created that arc, which means what does this have to be? That's all it is. Because the arcs are the same. The arcs are the same because the chords are the same. And it goes back to the reason that that works is because you could draw the radius in. So if that's 100, that makes this 100, which means these are the same, which means I can go this way, and I get 100 here, and these are the same. And that's why all of this works. Because you can draw in the radius and create isosceles triangles. And then you get all the correspondence out of it. Okay? Yeah. I bet you guys didn't expect to have this much fun right off the bat.
Oh, I'm so happy.
Hey, you have no braces. Congratulations.
Thank you.
It's a big day, isn't it?
Congratulations, I'm still wearing mine. All right.
It's a big day.
And I can't wait to take them off so I can have my...
Here's another one. So, excuse me. Now, I think the easiest way to do something here. Let's take this as a circle. And if I do this, and we leave it here where we have one chord drawn in. Now, if that chord is drawn in, and I wanted to cut it in half, basically if I wanted to bisect it with another chord, watch what happens. When you take to bisect this, what does it have to go through? It has to go through the center of the circle. Because no matter where you put a chord, no matter where you draw it, whether it's from here to here, if I want to cut that in half, I'd have to go through the center of the circle. That means that anytime you cut a chord in half, the other chord that you use is always called a what? Diameter. Okay? So what happens is, what happens then is that when you cut a chord in half, one of them is always a diameter. So this becomes, the diameter is always the perpendicular bisector of a chord. I think that's the easiest way to write that out, instead of words. And the more you look at it, the more you move, if you just look at a diagram, the more that you, wow. That. It has to be in the middle of it. Because chords, no matter where they're placed, you have to, well,
We know what you meant.
yeah. Never said I was good at drawing. Never said that. I tried. Okay? Thanks. Okay? If there's any other on this one. Bless you. Let's see if I can draw this one differently. So, excuse me. Let's say that we have two chords in a circle. All right? And if you draw from the center of the circle, so that it is equidistant. Remember, when you measure distance, you always want to measure the perpendicular distance because that's always the shortest distance between 2 points. Remember that, right? I know it's been a while since we've had a thing. Now, if I do that, what do you think has to happen with the two chords that are in red? Well, they have to be equal. They're gonna be congruent. They have to be. Watch what happens. If you draw this off to the side, those parts in green are all what? Yeah, they're all congruent, but they're all radius, right? Okay. Now, if those are all the same, and that means you get base angles that are the same. You okay with that? Now, if two angles in one triangle are the same as two angles in the other triangle, what has to be with the third angle? They have to be the same. They have to be the same. So then you get these two being the same. Not necessarily them being vertical, because they might not be. But then that means if these two are the same, that means these arcs are the same. And if the arcs are the same, the chords are the same. I know, exactly. And that's where all this comes back to. It all goes back to stupid triangles. Okay? So here's the deal. Whenever you have excuse me. Oops. Whenever you have in the same circle or in congruent circles, if two chords are congruent, if and only if, remember that? The if, that stands for if and only if. All right? If they're equidistant to the center, that's it. If they're the same distance to the center, the chords are the same. And because of that is because you can draw out all of those congruent triangles. Congruent triangles are really the whole basis of everything in a circle, which again sounds really, really weird that you're dealing with triangles and circles, but unfortunately, that's just the way how all of this works. Because that's how you can prove all of this. We should do some proofs.
No. You really unanimous no?
How quickly they turn on us, right? It's kind of funny. Okay. It's not bad. I'm trying to think. Well, you think everything's bad, except for 246. You got to think about that for a second.
No,
too.
it's 8-6.
All right. So what's going to happen a lot of times with these problems here, guys, is you can probably start to notice you're going to see a lot of the congruencies. You're going to see. I don't think there's really a crazy algebra, but you're going to have a lot of right triangles. Right triangles create Pythagorean theorem. Pythagorean theorem doesn't go away. Triples, those are just shortcuts. You always use Pythagorean theorem to get back to it? Yes, and from there. Could we make this extraordinarily complicated by figuring out, starting with arc length to work backwards into segments? Sure, we could, but I don't think we will. But just, there's a lot going on here, all right? Can I get to some examples then?
Not yet. I'm still confused.
No, you're just not writing anything.
No, my brain is actually shut down.
I'm sorry to hear that.
And it's all your fault.
I'll get over it. So this is going to be the type of stuff that we're going to be doing with all this information. They're going to ask us to find measures of arcs. They're going to ask us to find lengths of segments and things like that. What you're going to have to remember here is, well, in a circle you have only so many degrees. 360. So knowing that this part of the arc is 100 degrees, that means how much is left of the other two? 260. So both of these from here to here would be 260. But you need to figure out what one of them is. 130. Why is it just 130? Because the chords are the same, exactly. And that's where this comes from. It's just quick little subtraction, little division, nothing too fancy. So since these two chords are the same, that means these arcs have to be the same. Well, 130 and 130. And that's it. Right. You guys just worry too much.
It's always like this. And they're like, oh yeah.
Okay. I don't know why there's Sharpies here. So in this one, you have to do a little bit of thinking. What do you have to do first? Exactly. When you draw the other triangle, they're going to be congruent, which means what's the angle on this side here? 85. Is that a central angle? Does it intercept an arc? Is that arc to you? Which means the arc measure is 85. Yeah. RS would be 85, TU is 85. Yeah. So you're still waiting for the other shoe to drop. This should say, is the arc BC and arc CD congruent? Why? There's squares there, okay. More specifically, it's, what is CE? What's CE? The diameter. Is the diameter is perpendicular to the chord, right? So therefore, what does it do to that chord? Cuts it in half. So if it cuts the chord in half, what does it have to do to its arc then? It doesn't make the arc, it makes it the same, yes. It doesn't say that the arcs themselves are going to be 90 degrees. We don't know what the measure of the arc would be. Okay, we don't know that because we don't know how to. What's that? It wouldn't work. It would if it's not 90 degrees. That's a good question. So if it's not 90 degrees, it won't bisect that chord. All right, it has to be 90 degrees to bisect the chord. All right.
So what if we just had two intersecting chords, one of which is the diameter?
Then we'd have to do other stuff.
Yeah.
That's section 10.4. That's actually really easy. It's just chunk times chunk equals chunk times chunk.
Yeah.
So there's a lot of stuff that we'll be able to do. Okay. But yeah, if it's not 90 degrees, it won't work. All right, that's a good question. All right. Okay, should be no-brainer math here. No-brainer math. What does JK have to be? 55. Has to be, doesn't it?
No.
All right, what's GH? What is our, what's GH?
That'd be 135, sir.
Very good. Why is it 55? It's 55 because that's a diameter. It's perpendicular, which means these two segments are the same, which means these two chords are going to, I'm sorry, those two arcs are going to be the same. And the reason why I was asking why is this 135, because this is a diameter. Oops.
That'll be 125. Because
Oh, yeah, sorry. I can't math that.
I couldn't math it.
I apparently need more coffee than that. Correct. Angles, the only time we worry about the angles for right now is the central angles. When they're inside, their intercepted arcs are going to be different. There's rules for all that. We'll get it. We'll get it. Excuse me. Of course, we'll be at homework. All right, a couple more.
No.
I should change my contract.
Do you have any gum? No. Oh shit. I got it from my mom's mom, dead ass.
Nope.
No, I was looking at the console.
Are those two chords equidistant from the center? That means what about the chords then? If the chords are the same, their arcs are the same. What's the arc? Okay. So what is the only thing we haven't done yet?
Algebra.
Algebra.
And Derek.
Yeah, but remember, it's not that.
Hey, I wasn't done yesterday.
What's that? Sorry. I was just talking it through. I know. She was yelling at me, so I was just trying to be nice. What's that? Yeah, can't I still try to be nice? I mean, I can yell at you all day long if you want. Alright. So, oh no, there is algebra. We have to solve for x. I don't know what to do.
Set them equal to each other.
Exactly. Now, remember guys, a lot of this stuff does work out to be, it's a lot of set them equal to each other. There's a lot of solve for x like that, okay? In this example here, you know that those two chords, excuse me, those two chords have to be the same because their two arcs that they run into are the same. So there's going to be a lot of that going back and forth with this. So in this case here, we just have 4x minus 1 has to equal 3x plus 6. Two-step equation, or I'm sorry, not two-step, basically it's one quick step. Subtract the 3, 6, I'm sorry, subtract the 3x, add the 1, and you get?
X equals 7.
Get 7. All right. Notice you have 3 congruent arcs. If you have 3 congruent arcs, what will each of the arcs measure?
120.
120, good. The reason they have to measure 120 is because how many degrees are in a circle? That's all it is. So you'll see there's a lot of these little quick questions they can throw in here on. Once again, what do you think you need to wind up having to do? Don't forget, due to inflation this time around, it's $10 to say something nice about you at conferences, and it is now $25 to say something bad about a friend. What's up?
Mr. Murphy, come here. Are you serious? I got it. 40 bucks.
$40? Big spender there. All right, what do I do here? Sending to each other. Because that's really all we really can do right now. We don't know really anything else yet. We haven't gotten to that. So when all else fails with stuff today, just kind of send them to each other, see what happens. In this case here, when you start picking on the little guy, you'd move that 31 over, but what you do to the 16 at the same time? Add it back to the other side. So you're going to get 16 is 4x. X is. All right. Let me give you some problems. Give you a little bit of time. This is really rather quick. All right. If you guys give me a second after you write that down, I will put that up on the smart board so you can start working on it. You should be able to knock, I'd say 90% of that out before you leave today. Ladies and gentlemen, guys, there's stuff up on the board. Knock yourselves out.